All right, hi everybody, thanks for coming. This is Rhapsody in Zero Knowledge. My name is Tony Arcieri. I'm the co-founder of a company called Occlusion. Our name and our logo hints at our desire to move to zero knowledge protocols. So what this talk is about, this is a fairly complete history of zero knowledge proofs, as much as I can fit into a talk this long. It's also going to be a giant wall of papers, and for that I apologize, but hopefully you'll learn something. So what this talk is not is the math of zero knowledge proofs. So unfortunately, if you came here expecting to leave learning how to do the mathematics of zero knowledge proofs, that's not going to be the case. I did that deliberately because I've been to talks like that and they inevitably come out like this. So I'm also less of a mathematician, more of a historian and journalist, so I felt it would be better for both of us to just do the history. So to start this talk off with, I'd like to talk about this problem of identity theft. So it originates in two places. So there's data breaches, so people can't keep data secure. Unfortunately, a lot of that data they can't keep secure. Things like social security numbers, mother's maiden names. We have all these really lousy, insecure authentication methods that make it easy for people to steal their identity if that data gets stolen. And worse, companies engage in this sort of surveillance capitalism where they like to collect this data, risk these data breaches, and perhaps there are ways where they don't need to hoard this data to get the business value they want out of it. So what are some solutions? Well, we don't really have many. Like, one of them is you give your data to another company after the first company gets breached, and they monitor it, and then maybe they get breached too. So that doesn't seem to be working very well. Another is a move to stronger authentication mechanisms. These are things like national ID programs. But I feel, and many other people feel, that these have some rather frightening privacy implications. And to highlight some of those, I have a Pet Shop Boys song, if it'll work here.
If you've done nothing wrong, you've got nothing to fear. If you've something to hide, you shouldn't even be here. The whole project, it's brand new, conceived solely to protect you. Everyone has their own number in the system that we operate under. We're moving to a situation where your lives exist as information. You've done nothing wrong, you've got nothing to fear. If you've something to hide, you shouldn't even be here. You're a concern, you're a threat.
All right. So yeah, that was Integral by the Pet Shop Boys in 2006, shortly before the giant NSA debacle with Mark Klein, Bill Binney, and eventually Snowden would happen. So they were a little bit ahead of their time. So that whole thing, it's an allegory to this book by Yevgeny Zamyatin called We. This is the archetype for the modern dystopia. In this book, everybody is identified by a number and they're called numbers. But what it's really about is that QR code there embedded in the video links to this thing. So it was the UK in 2006 was pushing for this national ID card program. And several people pushed back against it, including Pet Shop Boys singer Neil Tennant, who quit his support of the Labour Party over it. You'll see a lot of text in there of the government officials trying to reassure us that there's no privacy downsides to this whatsoever. It's all for your benefit there, all to keep you safe. And right now, your telephone is broadcasting all sorts of numbers, all these static identifiers for you. This IMSI number, your mobile subscriber identity, your Wi-Fi MAC, and your Bluetooth identifier. And oh, by the way, there's this whole real ID thing coming. So if you have one of these, this will also have a RFID chip inside of there. So zero knowledge proofs offer a solution to this. What if we didn't have to sacrifice privacy to get this sort of security? So that's what this talk's all about. So what is a zero-knowledge proof? So we start out with a thing we want to prove. So in this case, we want to prove you found this guy. We want to prove you found him in zero knowledge. So say we have this typical puzzle. How do we prove in zero knowledge we found him? Oh, there you go. Yeah, we found him. So what you might be thinking is perhaps you can deduce his location based on his position relative to the edges of this mask paper. But hey, there's a solution for that too. You just kind of make this thing big enough so that you can't really figure any information out about where he's located based on that. So this is an idea called a proof of knowledge. So it consists of two things. So we've got a proof statement. This is the thing we want to prove, so prove you found that guy. And then we have something satisfying that proof. In the terminology of proof of knowledge, this is known as a witness. So a zero-knowledge proof is a proof where we can demonstrate we have that witness, but we don't reveal any information about it. So these two are really the main two behind the creation of this entire field. Shafi Goldwasser and Silvio Macaulay. I want to highlight Shafi in particular. In a recent poll among cryptographers, she was voted the most influential woman in cryptography, and yet I think nobody outside of cryptography has ever heard of her. If you thought this quote was pretty compelling, that's actually a Shafi quote. I had another one in the abstract for my talk. So much of this talk comes from Shafi's previous talks. I've kind of purloined a lot of her ideas and just learned a lot about the history of zero-knowledge proofs from her. So in 1982, Shafi and Silvio were working on this idea called probabilistic encryption and published this paper called How to Play Mental Poker. In this paper, they talk about replacing a trapdoor function, which is this idea from public key cryptography. So RSA is based on this trapdoor function where you know the factoring of the prime factorization of a number. So you replace it with probabilistic encryption, and you get this thing that works a lot like public key cryptography, where it is very easy to do if you know a particular magic number. And then the goal is it becomes easy to prove if you know that and hard if you do not. The entire field is based on complexity theory. So if you're familiar with complexity classes like P and NP, all these proof statements are generally in NP, but it's that same sort of field, but adapted into cryptographic applications. So what Shafi and Silvio wanted to do was go from this idea of probabilistic encryption to zero-knowledge proofs. And fortunately, creating an entire new field within cryptography is treated with a lot of skepticism. So probabilistic encryption was cool among the reviewers and publishers because it had the word encryption in it, but cryptographers don't generally do proofs. So this is a story of if at first you don't succeed, try again. So in the intervening years, they published many papers. They tried to publish this one. It was rejected. Next year, tried this one again. Rejected again. Its information content of proof systems rejected. Knowledge complexity of interactive protocols. Are we there yet? Nope. And it wasn't until 1985 that they published the knowledge complexity of interactive proof systems, which was pretty much the foundational paper for the entire field of zero-knowledge proofs. In this, they define what a zero-knowledge proof is. It is a proof whose witness reveals no additional information. This is a interactive proof system. So what is one of those? So if you go to Wikipedia, the page for zero-knowledge proofs, you might see this thing. But I don't think it really explains much, and Shafi hates it, so we're not going to do it. So instead, we're going to do something a little bit different. This is an example of proving knowledge of a graph 3 coloring algorithm. So in this example, we're going to have a couple people here. You might be familiar with Alice and Bob from cryptography, but in zero-knowledge proofs, we use a little bit different casts. So we got Peggy, our prover, and Victor, our verifier. So in this example, Peggy knows a 3 coloring algorithm for graphs. And what she wants to do is prove it to Victor, but prove it to Victor in zero knowledge. So we are going to throw little hats on all of the vertices of this graph after Peggy has colored it. And then what we're going to let Victor do is select an edge that he wants to reveal. Then we will reveal those 2 nodes. If they don't match, we've gained a little tiny bit of confidence that maybe Peggy's algorithm works. So we've gained this little insignificant amount. The actual formula there ends up being 1 minus the number of edges minus 1 over the number of edges. So not very much confidence, but a little. But what's cool is if we have Peggy recolor the graph, like so, and repeat this process over and over again, we will gain more confidence. So here's a cool little interactive web demo of this thing. And as we select more and more of these edges, we gain more and more confidence that Peggy's graph coloring algorithm actually works. So that same year in 1985, we had one of these interesting sort of like Newton-Leibniz moments where 2 people came up to with a very similar solution to the same problem. So this other one was called Arthur Merlin proofs by this guy Babai in this paper, Trading Group Theory for Randomness. So in this, his Peggy is King Arthur, and his his Peggy is Merlin, and his Victor is King Arthur. So this solves a slightly different problem. I'll get into that in a bit, but it had a few cool quotes and cool ideas. As it's waxing philosophical about proofs, one of the things it mentions is proofs are meaningless without a verifier. So even if you're mechanically checking a proof, something is checking your proof, but otherwise proofs are generally made to convince people of something. And additionally, zero-knowledge proofs in particular, you are trying to convince a distrustful party of something. So we really have a threat model around this sort of thing. So next year, in 1986, Shafi wrote a paper about both of these papers, kind of comparing them and showing that these 2 proof systems have equivalent proving power, but there was a subtle difference between them. It was this notion of public coin versus private coin. And just in case you're worried, you might have wandered into a blockchain talk. I will remind you this is 1986, and none of those things existed. So what's it talking about? So it's talking about a coin flipping protocol and how you would generate proofs about coin flips. So these fall into 2 categories. One is this public coin argument of knowledge, where the outcome of the coin flip is publicly visible to everyone. And then this other one, private coin, where you flip the coin in secret and want to prove that it was flipped according to some algorithm without revealing the outcome of the coin flip. So that same year, these 2 people, Fiat and Shamir, you might know Shamir as the S in RSA, published this paper on identity protocols and did something pretty interesting. they took one of these interactive algorithms and they turned it into a signature. So the important point about signatures is that they're non-interactive, so you're trying to prove something to someone offline. So the way they did this, so a interactive protocol would be structured by Peggy giving a commitment to Victor, Victor sending Peggy a random challenge, and Peggy sending back a proof that incorporates both the commitment and the random challenge. So to make this a non-interactive protocol, we need to get rid of that first round trip there. So the way they did that was they decided to compute the commitment with a random oracle, which is a fancy way of saying a hash function in this particular case. So they changed the protocol to be Peggy still creates a commitment, but we can replace the commitment with a hash, or we can replace the challenge with a hash of the commitment, and then Peggy still sends back the proof, and then this eliminates the need for Victor to participate in those first steps of that protocol. So this is a non-interactive public coin argument of knowledge. And this is the foundation of pretty much every modern digital signature algorithm, or at least the ones that are secure. So that's all well and good, but what about a non-interactive private coin argument of knowledge? So this would be far more interesting, right? So I'll get back to that, but one more very important thing from the 80s, 1988. We had basically the who's who of cryptography at the time write this paper that says everything provable is provable in zero knowledge. The TLDR of this is every problem in NP is a zero knowledge interactive proof, or in other words, zero knowledge proofs are universal. So getting back to that non-interactive private coin argument of knowledge problem, in 1992 we had one of the first foundational developments in this, and it kind of hints back to my original example there with the graph coloring. So the question they're trying to answer is, let's say you're given this, enormously large proof, right? Like some mathematician has given you a 100-page proof. You don't want to read the entire thing or check the entire thing. So how would you attempt to still ascertain whether or not this proof is valid? So they came up with this idea called probabilistically checkable proofs. So the nuance of this is the naive way of doing this in attempting to prove that you probabilistically proved you had checked enough of the proof to be sure, your proof would just kind of grow unboundedly. So really their fundamental core insight here was to create a proof whose size would not grow unboundedly while still allowing you to prove that you had checked enough of the proof to be sure. And this was kind of the entry point to this whole idea of how can we create smaller proofs. And then we got one of the two foundational advancements towards non-interactive proofs. So the first was by this guy, Joe Killian, and then the second would come in 1998. We see Silvio Micali again here, and he introduces this idea of computationally sound proofs. And yeah, many of these papers contain many of these interesting quotes, waxing philosophical about the nature of proofs. But he developed this notion of a proof which has polylogarithmic verification time, so it's efficient to verify. And these two papers taken together are the first example of something called SNARGs, or a succinct non-interactive argument. In 2001, we got something similar to Fiat Shamir, where Fiat Shamir worked in the random oracle model. This developed a new model for taking that interactive part of the proofs offline. So this was something called the Common Reference String Model, or CRS. You may have heard this referred to as a trusted setup. So you make this very large string using mathematics where if it's done in an untrusted manner, it can potentially be unraveled. So this is interesting in that it takes the proof offline, and it's a little scary in that it requires this initial trust to get the whole thing to work. In 2007, we got the first paper really describing a practical offline non-interactive proof system based upon this. And this is pretty much the foundation of everything else I'm going to present here. So in 2009, we got Bitcoin. Lots of people love Bitcoin. Bitcoin has a problem, though. It doesn't have any privacy. So Bitcoin was often originally described by people as being anonymous. They backpedaled on that and started calling it pseudonymous. To me, having worked in security for payments companies, I think pseudonymity doesn't really provide you much. This is easily revealed through techniques like graph clustering. So in 2014, a bunch of cryptographers who thought, the core ideas behind Bitcoin were a little bit interesting, but wanted to add privacy, got together and created Zcash. One of them was this guy, Elie Ben Sasson, and together they wrote this paper on zero cash. So zero cash is built on another oddly named idea called ZK snarks, or zero knowledge succinct non-interactive arguments of knowledge. So the zero coin paper wasn't actually where snarks were introduced, kind of glossed over that, but it was the first practical application of using them to solve this idea of shielded transactions, or how to hide payments on a public blockchain. So quick overview of ZK snarks. So they take these zero knowledge proofs and realize them as something called algebraic circuits, sort of similar to electronic circuits, but mathematical. This particular implementation used weird elliptic curves. So they have this weird property called the bilinear pairing property. So most elliptic curves we use just don't work with them. This operates in that common reference string model, so it required a trusted setup. And it fits into something called a rank 1 constraint system. So this describes a matrix in which all of these constraints fit, and you can think of each of these constraints as mapping to a single gate in that algebraic circuit. So a quick example of one of these constraints, how would you do Booleans with these constraints? So a constraint you can use to represent Booleans is x times x minus 1 equals 0. Another way you can think of this is x squared minus x equals 0. But there are only two valid solutions for this, so 0 and 1. So in 2015, Elie Ben Sasson wrote another paper on this idea of taking the special types of elliptic curves and creating something called a recursive proof. So this allows you to prove that you have knowledge of a previous solution to a proof. Or, yo dog, I heard you like zero knowledge proofs, so I put some proofs in your proofs. So these rely on something called elliptic curve cycles. So it requires you have two elliptic curves that have a special mathematical structure where they're kind of bonded to each other. So there is, elliptic curves have a scalar field. So the scalar field of one maps to the point field of another, and vice versa. So let me get back to that problem I was highlighting earlier of that trusted setup. So the Zcash people, in trying to launch Zcash, did all sorts of crazy things to get it off the ground. Like they ran this ceremony to create the common reference string with something called a multi-party computation, and then proceeded to destroy their computers in the hopes this would convince everybody that that sort of mathematical toxic waste of the trusted setup was destroyed. Unfortunately, this was insufficient. They accidentally leaked that toxic waste through the ceremony transcript, so they're trying to publish a transcript proving that they had done the process securely and accidentally leaked the toxic waste. So that was bad. So really, it would be great if we could just get rid of that. So they tried one thing that was kind of interesting. It was called powers of tau. The idea being that they could have this prolonged ceremony to have hundreds of people or more participate in the creation of this common reference string. Anybody here participate in powers of tau? Okay, just one. Then 2017, we finally got a couple good solutions. One is ZK Starks, which I'll talk about a bit later because the paper wasn't published till 2018. But first, I'll talk about bulletproofs. So bulletproofs are a type of non-interactive zero-knowledge proof. They have a small proof size, so kind of some of the properties of snarks. They don't have trusted setup, hooray, so they solved that problem. Also uses normal elliptic curves, so they aren't these weird ones that require bilinear pairings. They're ideally suited for range proofs. So the example I gave of Booleans and those constraints, right, that's kind of the degenerate form of a range proof. So a range proof can prove that a value is in a particular range without revealing it. This is important for zero-knowledge cryptocurrencies because otherwise somebody might give you a negative number instead of a positive one, and then you might think your transaction balances when really they just gave you negative money. The only drawback of these is the verification time increases with the number of arguments, whereas with snarks it's fixed. So 2018, we got that ZK Stark thing I was talking about earlier. So this is Elie Ben Sasson again. So ZK Starks are built on symmetric cryptography, which is cool because unlike elliptic curves, they will be secure in a world where a large quantum computer that can break the discrete log problem exists. So they also eliminate that trusted setup. So it uses this concept that's similar to erasure coding to try to generate the CRS in a way that no one can gain advantage in learning what it is. Uses a slightly more abstract and complicated model than these rank 1 constraint systems. It's called AIR. Probably the main drawback of these is they're mathematically quite complicated. We're still waiting on a production quality implementation, but fortunately, Elie Ben Sasson created an entire company to work on creating a production quality implementation of Starks, and they have their work in progress, libstark, up on GitHub. Also this year, we got something called the Coda protocol, which I think is pretty cool. So they built a proof of stake blockchain on recursive zero-knowledge proofs. So they have this fun little image there. So if you're building a database and you're doing log-based replication, as soon as your log is so far behind that your log is bigger than your entire database's state, that's the point at which you should probably switch to state-based replication, right, and just send the entire state. Normally, blockchains can't do that because they need the entire history to be proven. So what Coda did was apply these recursive zero-knowledge proofs, so they always get this consistent size proof that they have the longest chain. I believe there it says it's 22 kilobytes. So to me, this is pretty interesting research. So Coda proves longest chain through those recursive ZKPs. It's written in OCaml. Any OCaml fans here? A few of you. So they also made this cool thing called Snarky. So they made a compiler that will take a subset of OCaml and realize it as algebraic circuits by compiling it to this set of constraints. So this, to me, is this pretty awesome idea that we can compile programs into zero-knowledge proofs written in a language otherwise you might normally use. So 2019, we got kind of that idea on steroids with this thing called Zexy. So this is a similar idea of being able to do distributed verifiable computation, otherwise known as universal verifiable computation. So we can use zero-knowledge proofs to prove that any program, even given secret inputs, was executed correctly. And another neat thing you can do is run an encryption algorithm inside of this program so its outputs are encrypted to a particular key that you're interested in. Finally, last two papers here. The day my talk got accepted, this paper got published. So this is Spartan. Found a solution to creating ZK snarks that have no trusted setup. So that is great, and that is where our story would end, except for on Tuesday, there was a major new development, the system called Halo. So Halo is kind of the holy grail of what we've wanted out of zero-knowledge proofs forever. So Halo combines these best ideas of snarks and bullet proofs. So it gives us recursive proofs. Bullet proofs do not support recursive proofs. It doesn't require trusted setup. And it uses normal elliptic curves, so they don't need this bilinear pairing property. They still do that, use that neat sort of curve cycle property to achieve that. All right, so that's all I got, and thanks for coming. All right, I think I have time for some questions. All right, we got one over there. Perfect. So I'm probably not the person to ask about that. So most of them are in NP. You're saying like what would happen? Sorry, I forgot to repeat the question. So I think you were trying to ask if a solution to P equals NP were found, what effect that would have on zero-knowledge proofs. I don't actually know. Yeah.
You mentioned that you are actually making a venture to use some of these ideas. Can you tell us about that?
So we are working on a sort of bridge between the cryptocurrency systems we work on, which is called Cosmos, into the Zcash shielded pool. So Zcash has two sets of addresses right now. It has T addresses, which are transparent, and Z addresses, which are the zero-knowledge ones. So right now there's one way in and out of the Zcash shielded pool. So we're trying to make another way so you can move stuff in and out of the shielded pool directly from Cosmos.
How does zero-knowledge proofs and VS Code particularly like handle historical
So the question was, how does it handle verifying the history? So my answer to that is you don't have to, because it proves that the current state is correct. So to the extent zero-knowledge proofs work, they prove the history is correct. Yeah.
Are there significant scaling differences between the recursive proof algorithms you mentioned?
So yeah, questions about scalability of recursive proofs. I would say so we're trying to operate Coda right now. So it does add to latency. So the kind of publicly visible systems we work on generally come to consensus in about 6 seconds. Coda, they're working on figuring out what their latency target is going to be. So generating those proofs does take time, and it does add latency. The cool thing, though, is new nodes can sync up instantaneously because all they need is that 22 kilobyte proof. So it's a trade-off, I'd say. So yeah.
You mentioned earlier that you weren't going to talk about the mathematics behind it. Do you have any suggested resources for somebody who would be interested in that?
Yeah. So if you want to learn more, Vitalik Buterin has a great series of blog posts on his personal blog. There is also, probably should have found it and mentioned it, but there is an entire self-contained paper on zk snarks that assumes you know nothing else. It's about 75 pages long. Unfortunately, I didn't get its name before the talk. But anybody else? There you go. Okay.
Is there an intersection between zero-knowledge proofs and our current use of asymmetric encryption? And if there is, could you maybe describe what it would look like for us to be using these instead of our current public-private?
Yeah. So something this would allow you to do instead of, the question is, I guess, what could we do with zero-knowledge proofs that's like public key cryptography but better? So as I was talking about these national ID programs, you could do things like prove non-inclusion on the no-flight list without revealing who you are. So you could just generate a proof on the fly that says, I am not contained within this log. You could prove your age, something like that, right? So if there are properties encoded in, let's say, an anonymous credential that somebody has issued you, you can select which ones you want to reveal only those, and you can do this kind of non-interactively without going back to your certificate authority or issuer of a credential. All right, I think that's it. Thanks for coming, everyone.